a long one. I'm on my last power, so I don't know if we're going to make it here. Okay, this is part 148. It's line 18A, 3Z2A, 3B. Again, the last video was 3A, so 3B is basically I divided it up, the data up, into 2 videos for this particular topic, okay? So this is evidence of supersymmetric Higgs mass CMSSM SUSY Wow Seti. Oh, I actually found evidence about it. Yeah, I did. This is test results for people. So this is the Wow Seti signal here. So I googled Higgs with the mass to find out if anybody had anything new for me to look at. And this came up, high energy physics, phenomenology, 119 to 125 GeV Higgs from a string derived slice of the CMSSM. It's from L. Arporcio, D.G. Sardino, Ali Abanez. Submitted February 3rd, 2012, which was 2 days before the last guy wrote that he wasn't sure that it could be proven, and yet someone else says they have. Okay? So, the recent experimental hints for a relatively heavy Higgs with a mass in the range of 119 to 125 GeV favor supersymmetric scenarios with a large mixing in the stop mass matrix. Sorry, I'm having trouble with my voice. It has been shown that this is possible in the constrained minimal supersymmetric standard model, CMSSM, but only for a very specific relation between the trilinear parameter and the soft scalar mass A, and sizable values of tan beta. We describe here a string-derived scheme in which the first condition is automatic and the second arises as a consequence of imposing radiative EW symmetry breaking and viable neutrino dark matter in agreement with WMAP constraints. More specifically, we consider modulus dominated SUSY breaking in type 2 string compactifications and show that it leads to a very predictive CMSSM-like scheme with small departures due to background fluxes. Imposing the above constraints leaves the only parameter which corresponds to an overall scale. We show that in construction I'll let you guys read this. I need to rest my voice for a minute. Leads to 119 GeV, 125 GeV, okay? We determine the detectability of this model and show that it could start being probed by the LHC at 7-8 TeV with a luminosity of that, and the whole parameter space would be accessible for that. Okay? Furthermore, this scenario can host a long-lived star with the right properties to lead to catalyzed BBN. We finally argue that anthropic arguments could favor the highest value for the Higgs mass that is compatible with neutrino dark matter, i.e. that. This is high energy physics phenomenally. There's the report number. And there's the website. David G. Sardino. And he has an email as well. It's on arxiv.org/abs/1202.0822. So we can look at the pretty pictures here. I'm not sure. This is some sort of collision with a boson. This is the preliminaries. Let me show you it real quick here, close up. I like the bright colors you guys use. They look nice. And there's that. And that. The lepton. Whatever that means. Here's a Tevatron Higgs sector reach CMS. Okay. I'll let you guys read it. I know capiche. Oh, more pretty colors. And there's tan. And then I'm losing my voice. Better not. I have another 100 videos to go. Okay, each point in the graph which has the A boson mass on the horizontal axis and the tan beta parameter on the vertical axis for the constrained MSSM scenario represent a different choice for some of the parameters allowed to vary within their possible range. The experiment's possibility to further extend their efficiency to collect Higgs bosons. And I got that from www.science20.com Quantum Diaries. So take a look at their website. They got a lot. There's a lot more graphs there, a lot more information. I just pulled a few things, okay? Here's another pretty graph to look at. Charged LSP, and MO and M1/2. This is DM favored regions in the universal Gaussian and S fermion mass parameters of the CMSSM, with the 4 benchmark points adopted for the study of 13 and 14. Again, more figures. And it's iopscience.iop.org. They've come up before, by the way. They have a lot of good stuff. This is an interesting picture here. And I don't know what that is. D-jet mass. There's the E plus E minus. I've seen that before. It was for linear equations or linear laser beams and stuff. A 1 TV display of an event and right D-jet. There's my little black bugs that keep bugging me for my plants. Aren't they cute? Yeah. Bye-bye. I tell them don't go on my screen. Invariant mass distribution. Okay. And that's isopscience.iop.org. And there's another scenario where mass relations among SUSY particles set their Rayleigh density in the so-called coannihilation region. Here is the small mass splitting between the neutrino and another SUSY particle to enhance the neutrino annihilar cross-section. It's got something to do with these things. This region is of special interest in view of the anomalous positron abundance in the cosmic radiation reported by Pamela. I didn't look up Pamela. I don't know what that is. The WIMP mass could be measured to relative accuracy of that, depending on the availability of beam polarization. Again, we use a beam with our UFO thingy. So here's the P-flow photons and E plus, E minus stuff. Some sort of graph. So, WIMP. It talks about the weak signals. WIMP signals, which is the same, I think it's the same constitution as neutrinos. They have a weak signal with them. They don't interact with each other. WIMP signal seen as an WIMP signal seen as an excess of events. He's a persistent little bugger. Bye-bye. Go away. Go play in the plants. WIMP signal seen as an excess events in the single yeah, my little pet bugs. Photon energy distribution due to the E plus E blah blah blah. There, you guys read that. SM background, both beams are assumed to be polarized. What we expect to learn from E plus E minus collider is not limited to inferring the DM Rayleigh density. Rather, the precision measurement of the DM candidate properties and interactions will allow to fix the particle physics of DM, and then attempt to move forward Euclidating its role in cosmology. This addresses key questions, such as testing standard Big Bang cosmology back to 10-9s, at which time the DM Rayleigh density was produced, and determining the local DM density profile in the galaxy. In turn, these data are essential in the interpretation of direct DM detection experiments, which are pushing their sensitivity closer to the region where SUSY predicts the observation of a signal. If DM is due to a weakly interacting, massive new particle, an E plus E minus linear collider, a sufficient energy is expected to measure its properties with the precision needed to perform crucial model-independent tests in conjunction with satellite and DM direct detection experiments. Today we do not know with precision what the required collision energy is. Oh, Okay, so that's what the problem is. The LHC will likely provide us with an answer if NP, such as SUSY or EDS, is indeed responsible for cosmic DM. With the first LHC results in hand, proceeding with the construction and operation of a high-energy, high-luminosity linear collider will open up the path towards a new fascinating era of fundamental science. I believe there was a brand new one just built in Germany. I'm not sure if that's what it is. I'm running out of time here. Okay, so there's the collider study. My thoughts. As we go along the lines of data, I'm learning more and more things that's slowly starting to make sense. Remember I told you it takes about 5 videos to figure this out? In this case, it's going to take 100 videos. I know back in earlier lines there's lots of talk about B mesons, WIMP signal, and how people have figured out how to get smaller particles to interact with one another in their test results. Bell, Super B, Eric, Opal, CERN all bring up data about the mesons. It's impossible for you to look up the words. There's the tags. And back to this, it's the role of E plus E minus linear collider in the study of cosmic matter from M. Battaglia, April 2009. Abstract, the potential of a high energy, high luminosity E plus E minus linear collider in the